Hello all, myself Bendi Gautam Maharaj. I am here to present my assignment on the topic particle physics. Okay, and let us start with our assignment. And here it goes. Coming to the introduction, particle physics, also known as high energy physics, is a branch of physics that delves into the fundamental constituents of the universe and their interactions at the smallest scales. It seeks to unravel the mysteries of matter, energy, space, and time by exploring the elementary particles that make up everything around us. At its core, particle physics aims to answer profound questions about the nature of reality, the origin of the universe, and the fundamental forces that govern its behavior. The exploration of particle physics has given rise to Standard Model, a comprehensive theoretical framework that classifies and describes the known elementary particles and their interactions. This model has been remarkably successful in explaining a wide range of phenomena from the behavior of particles in accelerators to the dynamics of the early universe. Here are some of the key points that we are going to discuss. Some among them are elementary particles. These are the First one, sorry, elementary particles. These are the building blocks of the matter and include quarks, leptons, and force carrying bosons. Understanding their properties and interactions is fundamental to unraveling the fabric of the universe. Second one, forces and interactions. Particle physicists study the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Exploring how particles interact through these forces provides insight to the underlying principles of the cosmos. Third one, symmetries and conservation laws. Symmetry principles guides the formulation of theories and the conservation laws, such as the conservation of energy and the momentum, govern the behavior of particles in various interactions. Fourth, experimental methods. Particle physicists utilize advanced experimental techniques and powerful accelerators to study particles at extreme high energies. These experiments offer glimpses into the excuse me, behavior of matter under extreme conditions, shedding light on the fundamental principles that govern the universe. Fifth one, cosmic connections. Particle physics also explores connections with astrophysics and cosmology, investigating the role of particles in the evolution of the universe, the formation of galaxies, and the existence of dark matter and dark energy. Now, coming to the main another section, particles and antiparticles. Particles. Particles are the fundamental building blocks of matter and they play a central role in the field of particle physics. These entities can be categorized into two main types: elementary particles and composite particles. Elementary particles. These are the particles that are not composed of smaller constituents. The standard model of particle physics categorizes elementary particles into two groups. They are fermions and bosons. Fermions, these are the particles that make up matter. Quarks and leptons are types of fermions. Quarks combine to form hadrons, such as protons and neutrons, while leptons includes particles like electrons and neutrinos. Bosons. These particles are force carriers that mediate fundamental forces. For example, the photon mediates the electromagnetic force and W by Z excuse me, bosons mediate the weak nuclear force. Coming to composite particles that are called as also called as hadrons. These particles are composed of smaller building blocks called quarks. Hadrons are divided into two categories: baryons and mesons. Baryons, Examples include protons and neutrons. Baryons are made up of three quarks. Protons consist of two up quarks and one down quark, while neutrons consist of two down quarks and one up quark. Coming to mesons, mesons are composed of one quark and one antiquark. They are responsible for mediating a strong force that binds quarks together. Now, antiparticles. For every particle in the standard model, there exists an antiparticle with the same mass but opposite charge. When a particle and its antiparticle come into contact, they can annihilate each other, converting their mass into energy. This process is a fundamental aspect of particle physics and is observed in experimental contexts. Example: the antiparticle of an electron, alias a lepton, is called a positron. Positrons have a positive charge in contrast to the negative charge of electrons. When an electron and a positron encounter each other, they can annihilate, producing gamma ray photons. Coming to the next section, classification of particles. Particles in the universe can be broadly classified into three main categories: hadrons, leptons, and bosons. First one, hadrons. Hadrons are composite particles composed of quarks held together by the strong force mediated by gluons. There are two types of hadrons: baryons and mesons. As we discussed before, baryons are the hadrons made up of three quarks, protons and neutrons, which constitute the nucleus of atoms, are examples of baryons. Baryons of Baryons have baryon numbers of plus 1. Mesons. Mesons consist of one quark and one antiquark. They are responsible for mediating the strong nuclear force that binds quarks together. Mesons have baryon number of 0. Second one, leptons. Leptons are elementary particles that do not have any internal structure. That is, they are not composed of quarks. There are six types of leptons grouped into three generations. The first generation includes electron and electron neutrino. The second generation includes muon and muon neutrino. Third generation includes tau and tau neutrino. Leptons interact via the weak force and gravity, and they have lepton numbers associated with them. The third one, bosons. Bosons are force carrying particles that mediate the fundamental forces in the universe. There are several types of bosons. Photon mediates the electromagnetic force. W plus, W minus, Z naught. Bosons mediate the weak nuclear force responsible for processes like beta decay. Gluons mediate the strong force that bind quarks together inside hadrons. Higgs boson H naught associated with the Higgs field, it gives mass to particles through Higgs mechanism. Understanding particles and antiparticles is crucial for comprehending the interactions and transformations that occur at the smallest scales in the universe. The study of these fundamental entities has led to the development of the Standard Model, which provides a comprehensive framework for understanding practice particle physics phenomena, and also understanding the classification of particles is essential for comprehending the diverse nature of matter and the various forces that govern its behavior. This classification lays the foundation for the more detailed exploration of particle interactions and the underlying principles of particle physics. Coming to the next section, conservation laws. Conservation laws are fundamental principles in particle physics that describe the behavior of particles in various interactions. These laws As said, the certain properties of a system remain constant over time, providing valuable insights into the underlying symmetries and dynamics of particle interactions. In this section, we are going to look upon the definition of the lepton, baryon, and the isospin. And also, we'll be going to see the conservation rule for the respective conservation laws and also an example of the same. First one, conservation of lepton number. Leptons. Leptons are a group of elementary particles that includes electrons, muons, and tau particles along with their associated neutrinos. Conservation rule here is the total lepton number in a particle interaction remains constant. In other words, the sum of the lepton numbers before and after an interaction is the same. Example, in a beta decay, a neutron transforms into a proton emitting a beta particle, that is an electron and an electron neutrino. The total lepton numbers remains conserved. The second law, conservation of baryon number. As we have seen, baryons are hadrons composed of three quarks such as protons and neutrons. Here the rule is the total baryon number in a particle interaction is conserved. Baryon number is assigned plus 1 for baryons and 0 for other particles. Example, in nuclear reactions, the total number of protons and neutrons before and after the reaction remains the same, conserving the baryon number. Coming to the third one, conservation of isospin. Isospin is a quantum number related to the symmetry between protons and neutrons. It was initially introduced to explain the similarities between these two types of baryons. Here, the rule states isospin is conserved in strong nuclear interactions such as the interactions between protons and neutrons. Example, in certain nuclear reactions, protons can transform into neutrons and vice versa, while conserving the isospin quantum number. Conservation laws here provide crucial constraints on particle interactions, excuse me, guiding the formulation of theoretical models and helping experimental physicists to interpret observed phenomena. These laws highlight the underlying symmetries in the physical laws governing particle behavior. Understanding these conservation laws is essential for unraveling the intricate nature of particle interactions and ensuring that theoretical predictions align with experimental observations in the realm of practical particle physics. Coming to the next section, symmetry in particle physics. Symmetry principles play a crucial role in understanding the fundamental forces and particles in the universe. In the realm of particle physics, symmetries provide powerful tools for describing and predicting the behavior of particles and their interactions. Two significant symmetries in this context are SU2 and SU3 symmetry. The first one, SU2 symmetry. Here, SU2 stands for special unitary group of degree 2, which is a mathematical group that describes certain symmetries in quantum mechanics. Isospin symmetry. SU2 symmetry is a particular relevant in the context of isospin, a quantum number associated with the symmetry between protons and neutrons. Isospin doublet. Protons and neutrons, despite having different electric charges, can be considered as an isospin doublet under SU2 symmetry. This symmetry helps explain the similarities between these two types of baryons. Weak force interactions. SU2 symmetry is also manifested in weak force interactions, where W plus, W minus, and Z naught bosons mediate processes like beta decay. Second one, SU3 symmetry. SU3 is a mathematical group that describes a higher degree of symmetrical symmetry compared to SU2. It is relevant in the context of the strong force that binds quarks together. Flavor symmetry. SU3 symmetry is associated with different flavors of quarks: up, down, charm, strange, top, and bottom. Octet and decuplet representations. Quarks are organized into representations of SU3, with the most common representations being the octet and decuplet. These representations helps explain the properties of mesons and baryons, gluons, and quantum chromodynamics. SU3 symmetry is a fundamental to understanding the strong force, which is mediated by gluons. This force is described by quantum chromodynamics QCD, a component of the standard model. Symmetry principles are deeply intertwined with the laws governing particle interactions and they simplify the mathematical descriptions of complex physical phenomena. The exploration of these symmetries has led to a deeper understanding of the forces that shape the subatomic world. In summary, SU2 and SU3 symmetries are essential components of the theoretical framework in particle physics. Nature of particles, providing value insights into the nature of particles, their interactions, and the forces that govern them. Coming to the next section, qualitative introduction to quarks. Quarks are fundamental particles among the smallest building blocks of matter and play a pivotal role in the standard model of particle physics. They possess unique properties that contribute to the diversity and structure of particles observed in nature. Here are some properties of quarks. Flavors of quarks. Quarks come in six different types or flavors: up, down, char, strange, top, and bottom. Each flavor has its own distinct properties such as mass and electric charge. The up and down quarks are the most common and stable, making up the protons and neutrons found in atomic nuclei. Fractional electric charges. Excuse me. Quarks exhibit fractional electric charges. For instance, up quarks carry a charge of plus 2 by 3 electron, where E represents the elementary charge, while down quarks possesses a charge of minus 1 by 3 E. This fractional charge property contrasts the familiar integer charges of electrons minus 1e and the protons plus 1e. Color charge. Quarks possess a property known as color charge, which does not refer to visible color but to a quantum property akin to the primary colors in a mathematical sense. Quarks can have three color states: red, green, and blue, or the corresponding anticolors anti-red, anti-green, and anti-blue. This color charge is fundamental to the strong nuclear force described by QCD quantum chromodynamics, which binds quarks together within hadrons, like nucleons. Confinement. Due to the nature of strong force, quarks are confined within composite particles called hadrons and cannot exist in isolation. When quarks are pulled apart, the energy increases and new quark antiquark pairs are created, forming new hadrons. Understanding quarks and their interactions not only unveils the complexity of particle physics but also provides insights into the fundamental forces shaping the universe. Quarks' unique properties and behavior offer a deeper comprehension of particle interactions, contributing significantly to our understanding of matter at its most fundamental level. Coming to the next and last section, structure of hadrons. The structure of hadrons, which include baryons such as protons and neutrons, and mesons, is closely tied to the behavior of quarks, the strong force mediated by gluons. Understanding the internal composition of these particles is crucial for unraveling the mysteries of the strong force and comprehending the nature of matter at the subatomic level. First type, protons and neutrons, or together can be called as baryons. As we have already seen, baryons are hadrons composed of three quarks. The most well-known examples are protons and neutrons, which are fundamental components of an atomic nuclei. Here, the quark composition. For a proton, it is composed of two up, up quarks and one down quark, UUD. Neutron is composed of two down quarks and one up quark, UDD. Strong force and gluons. The strong nuclear force described by quantum chromodynamics QCD binds quarks together with baryons. Gluons are the forces carry for the strong force and they mediate the interactions between quarks. Color charge. Quarks carry color charge red, green, or blue, and the color neutral combination within baryons ensure their overall colorless. Coming to the second type, mesons. Mesons are hadrons composed of one quark and one antiquark pair. Quark antiquark interactions. Mesons are formed by the strong force interactions between a quark and an antiquark. The exchange of gluons mediates this interaction, leading to the binding of quark antiquark pair. Color charge. Similar to baryons as we have seen just now, mesons are also color neutral overall. The combination of a quark and an antiquark ensures the neutrality. Mesons in the strong force. Mesons play a crucial role in mediating the strong force between quarks within hadrons. Decay of mesons. Mesons are unstable and undergo decay processes. The decay typically involves the and annihilation of the quark antiquark pair, leading to the creation of other particles. Understanding the structure of hadrons provides insights into the behavior of the strong force and the dynamics of quark interactions. Quantum chromodynamics QCD is a theoretical framework that describes the strong force and the behavior of quarks and gluons. Invest- Investigating the properties and interactions of hadrons is essential for advancing our understanding of the fundamental components of matter and the forces that govern their behavior at the subatomic scale. And this ends my topic. And also, let me conclude the topic. As technology nowadays advances, particle physicists continue to push the boundaries of our understanding, seeking answers to questions that transcend the limits of classical physics. The exploration of particle physics not only our knowledge, deepens our knowledge of the fundamental forces at play, but also opens new frontiers in science and technology with implications of our understanding of the universe past, present, and future. Thank you. This concludes the assignment.